Hello, this is Jingwei from National University of Singapore. It's a pleasure to present our workshop paper, BOSSA, Learning Music Style through Cross-Modal Bootstrapping. This is a joint work with Zhiyuan, Gaxia, and Yewang. Our motivation is like this. Suppose you have some music idea in mind and you want to share it with other people. What would you do? Perhaps you could try to describe it using text. For example, I want a steady, catchy groove of electronic pop music. However, a potential problem here is that text description could be not accurate enough. So that in this case, you might want to further sing it out so that the other people could hear what you think about. So our perspective is like this. Music style is inherently implicit and is better heard than described. So in this work, we propose a cross-modal framework. This framework learns implicit music styles from raw audio, and after that, to apply the audio style to symbolic music arrangement. Our model is inspired by the BLIP2 architecture. In this case, the input is an image and the goal is to generate a text description based on that image input. Our framework adopts a similar design. In the first place, we leverage two established pre-trained music language models. The first one is in the audio domain and the other is in the symbolic domain. These language models are frozen, and our purpose is to leverage their established music understanding and capability. In the middle, we introduce a queue format, which is essentially an interface module. This module will first extract a set of style representation from the audio hidden representation. And after that, this style representation will be used as prompt to encourage the symbolic language model to generate piano arrangement. And this whole model will be trained via two stages. In the first stage, our goal is cross-modal music representation alignment. Here is a zoom-in view of the queue format. At training stage, this model takes the input of three inputs. The first is an audio, the second is a symbolic clip which is paired to the audio, and additionally, the input includes a set of randomly initialized query embeddings. These query embeddings will be attending to the hidden audio representation through cross-attention. And on the left branch, our goal is to extract a set of representation Z, which is informative of the auditory music style from the left side. The right branch is mainly used for supervisory purpose to realize cross-modal alignment. When the model is well trained, we will discard the right-hand side branch and only retain the left-hand side audio branch. In the second stage of our model training, we are going to fine-tune a symbolic music language model. This language model takes two inputs. One is the hidden style representation Z extracted from the queue format, and another is a set of lead sheet tokens which prescribes the content on top of which we want to arrange piano arrangement. And this model is trained to autoregressively reconstruct the piano arrangement tokens conditioned on the two inputs contents. Here is more detail of our model configuration. Our audio language model is MusicGen, and the symbolic language model is MusicCoco. Both models have more than 1 billion trainable parameters, but in our case, these parameters are kept frozen. The only trainable parameters comes from the queue format, which is less than 200 trainable parameters, which is still manageable. To train such a model, we primarily leverage two training data. The first is the Pop 909 dataset, which contains 1,000 music pieces with both orchestrated audio and symbolic piano arrangement. And another dataset is PIAST, which is a piano transcription dataset. The reason why we incorporate here is that PIAST contains more diverse music genres, and we hope our model to be more generalizable to more music genres. At inference time, we consider two additional test sets, Ballroom and GTZan. Both datasets contains music clips of varied orchestration and music styles. Here is a demonstration of what our model can do. Given an input music audio clip, in the first place we'll use SheetSage to transcribe the lead sheet. The lead sheet will be further leveraged as the content by our model, and our model also takes in the audio and get the style directly from the audio. Based on that, our model can further generate a piano cover for the input music audio. For example, here we have a jive music. The transcribed lead sheet is like this. And our piano cover result. We also have the result from the baseline model. In this case, the baseline model reconstructs the melody very faithfully. However, the texture of the music, the general style, sounds more like pop than jive music. In comparison, our model is able to produce the style more accurately. Here we have another set of examples, tango music. Let's listen to the baseline result first. And our result. Besides making piano cover generation, our model is also capable of style transfer. In this case, the content lead sheet and style from example audio does not necessarily come from the same music piece. For example, here we have a lead sheet content from this piece. We can arrange it in the style of samba music. And ragtime. We can also imagine how Franz Liszt might play this piece on piano. To wrap up, I want to highlight a little bit about our broader vision of our research. Previously, we have mainly focused on symbolic music arrangements, and in this work, it is the first time that we can let user specify an audio example and extract style from that audio to directly collaboratively control the music arrangement they want. So, in our future research, we hope to bridge the loop from music analysis to generation so that we can look forward to a more stylistic, structured, and collaborative music arrangement. Thank you for your attention.